Welcome to the session. I am Dr. L. Vanitha, Professor, ECE Department of SAEC Engineering College. Today's session we are going to see about genetic algorithm for problem solving. Generally, the problem solving techniques consist of two types. One is hard computing techniques and another one is soft computing techniques. We'll see what is computing. So the process of completing a task with the help of a computer generally we define as a computing device. In this category we have two types. One is hard computing and another one is soft computing. And the hard computing is suitable for mathematical problems. Generally the real world problems is very difficult to solve and it also consumes a large amount of computation time and cost. Comparatively, the soft computing generally it is used to solve non-linear problems which involves uncertainty. Generally, this type of computing is applicable for real life problems which requires a lot of intelligence to solve it. The soft computing, we are going to see about the soft computing techniques. So this under the soft computing techniques, we have three categories, major categories, which is fuzzy logic, artificial neural networks, and evolutionary algorithms. So under the topic which we are going to see today, that is genetic algorithm, comes under the category of evolutionary algorithms. So we'll see the details about the genetic algorithm. Let us see the definition for a genetic algorithm. So this genetic algorithm that solves a problem by finding optimized solution based on the theory of natural selection. So the core idea behind this genetic algorithm is natural selection. So this type of algorithm is excellent for searching through large and complex data set. So if the data set is very large, then this is a beautiful algorithm which finds a solution which finds a reasonable solution. So generally for complex problems, it finds a reasonable solution. We'll see what is actually happening in genetic algorithm. We'll see with the help of the flowchart, we'll see what is actually going behind this genetic algorithm. Initially, we'll have possible solutions. So there will be that we call it as a population. So generally, we have huge solutions. So possible solutions will be huge. That we call it as a initial population, and we generally have a fitness algorithm to evaluate this solution, which is the best solution. So to evaluate that, we'll have a fitness algorithm. So by means of that fitness algorithm, the fitness of that solution is evaluated, and when the result converges, suppose if the result converges, that process comes to an end. Suppose if the result doesn't converge, then we go to a series of steps. So that will consist of a selection, mutation, crossover. It may be one step or combination of these steps. Either selection, mutation, crossover, we can combine the steps, or either one of the steps may be used. And we form actually from parent 1 and 2, actually the solution, possible solution, what we derived, that we call it as a parent 1 and 2. And from that parent, we select children. So based on after the operation of selection, mutation, crossover, children are formed. So this children will be evaluated. Again, the process repeats. It is evaluated for fitness. So after the evaluation, if the result converges, then the process ends. Suppose if the process doesn't end, then again the process repeats. The cycle repeats again. Let us see with an example. Let us try to understand the genetic algorithm with an example. The very famous algorithm, traveling salesman problem, is everyone knows. That is usually the problem. Usually we find that is considered to be the real life problem, and solution. Generally, any algorithm which is developed, we try to find the solution for that problem. So in this case, we consider 4 cities. We take a simplest case to understand the concept of genetic algorithm. So there we consider 4 cities, cities 1, 2, 3, 4, and we also assume that the cost of travel between the cities are known. So we'll consider these 2 cases. So 4 cities, we name it as 1, 2, 3, 4, and cost of travel between the cities is known. So that is our objective, and it is not directional. That means the cost between, suppose for example, the cost between 1 and 2 and 2 and 1 is going to be the same. And so the objective, so what is the objective of the solution? So what is the objective for our problem? So what is the solution we are going to find out? What we are going to find out is all cities should be visited but only once. So all cities should be travelled but only once, and the total travelling cost should be minimum. So these two are the main objective. So let us take this example. So we can see that diagram. So we have 4 cities. City 1, 2 and 3 all are connected. Remember that this is not directional. That means direction between 1 and 2 and 2 and 1 is same. And that means cost is same. So we can see here the cost of travel between 1 and 2 is 10, and 2 and 3 is 20, 3 and 4 is 30, and 4 and 1 is 40. And we can see here that there is also a path between 1 and 3. And the cost is 15. So it is very important to note here is there is no path between 2 and 4. It is very important to note, to make a note of it, that there is no path between 2 and 4. Let us take an assumption that fitness function. So we have to evaluate the fitness function. Let us take that fitness function to be summation of travelling cost. So we are considering the fitness function to be the summation of travelling cost. Let us evaluate it. So you can see that we have a path 1, 2, 3, 4. The first one, that is 1, 2, 3, 4. We are calculating the fitness function. So you can see here that the cost of travel between 1 and 2 is 10, and 2 and 3 is 20, 3 and 4 is 30. It is added 10 plus 20 plus 30, it is 60. So similarly we are finding the possible solutions that we call it as a population. So it is 2, 3, 1, 4. 3, 2, 1, 4, 4, 1, 3, 2, and we are calculating the fitness function. Now, based on the fitness function, we are ranking it. We are putting a rank. So, rank is based on the fitness function, that is the value. So, whichever is the least value, we call it as rank 1. So, here we can see that the least value is being 60. We name it as 1. We can see that the next rank is, that is the next least one is 70. We are naming it as 2. Now we can see that the next least one is 75, and we name it as 3. We give the name 3 for both. We can see that the 2 fitness function comes to 75, and we name both as 3. So this is the table which is created. So this is the table we have created. Now we proceed to iteration 1. So now the process starts. So now it is iteration 1. So iteration 1 begins. So the first step is to select the parent. Now we need 2 parents. We need 2 parents which has to be selected from this table. From this table we have to select 2 parents. So naturally what is our aim will be to select the least value. So rank 1 and 2. Generally that will be our opinion. So let us select 1 and 2. Rank 1 and 2 is selected as parent 1 and 2. So you can see here 1, 2, 3, 4 and 3, 2, 1, 4. So that is selected as parent 1 and parent 2. So you can see here that parent 1 we have selected, so first one is selected as parent 1 and third one is selected as parent 2. So based on the rank we have selected. So this generally we give the name as tournament selection. So in the tournament we name it as rank 1 and 2. No? So like that this method we call it as tournament selection. There are many methods. One of the method we are following is tournament selection. So this by this method we have selected parent 1 and 2. Next step we are going to apply crossover. So in this there are many methods in this crossover. We are going to apply some 2 methods and we are going to form the children. So from the parent we are going to apply some crossover methods. In crossover we have different steps. So we are going to apply that and we are going to form the children. So in this crossover we are going to follow two sub steps. In this crossover we are going to perform 2 sub steps to obtain the children. So in this first we are going to exchange the cell. That means we can see that in the first one 1, 2, 3, 4 the 4th cell and the first cell is swapped. So the 4 and 1 is swapped. Similarly from the parent 2 the first and the 4th one is swapped. The first and the 4th one is swapped. So this is the first step. In the second step, the center one, that is center cell, second and third cell is swapped between parents itself. So first we are swapping between the parent itself, parent 1 itself we are swapping, and second step we are swapping between parents, parent 1 and 2. So this we are doing. So you can see here it is when we are swapping between parent 1 and 2, you can see here that 2 and 1 goes to parent, from parent 2 goes to parent 1, and 2 and 3 from parent 1 comes to parent 2. So, as a result, we have obtained two children. One is 4211 and another child 2 is 4233. But unfortunately, you can see here that cell repeats. See here, 1 repeats and there is 3 is missing. So, but it should not be like this. So, actually, when you obtain a child, it should be perfect. We know the children should be, we expect to be a perfect child. So, what we do, we are going to replace, the repetition is going to be replaced. So, one randomly, we can take any one randomly. So, from the first child, the one of the cell, that is a child 1, fourth cell, we are replacing by 3. It is only randomly we are doing. So, there is no hard and fast rule. So, we are doing randomly. Similarly, from child 2 also we can see that 3 is repeating. So, naturally 1 is missing. So, what we are going to do is, we are going to replace 3 by 1. So, this crossover process is over and we obtain the child. So, after the result, we can see that two children are obtained, 4213 and 4231. But remember, I hope you remember when I said the first problem when we discussed, when we saw that, I saw that there is no root between 4 and 2. So I think I hope you would have noted that there is no root between 4 and 2. So here if you see 4, 2, 1, 3, that means no root between 4 and 2. So this also child 1 has 4, 2, 1, 3. Child 2 also has 4, 2, 3, 1. That means both the solutions are not possible. So both the solutions are not possible. So both children are not acceptable. So this is a wrong solution. So iteration 1 fails. So what we are going to do is, the iteration is going to repeat again. We are going to repeat again. We have to start from the beginning. So child, the derived child is not possible. So next iteration, we are going to repeat the iteration. Iteration 2 starts. Again, we are going to select 2 other parent from the table. Let us look at the table again. So in this table, 1, 2 we have already selected. Now let us go for the other 2. So the remaining 2, that is 2, 3, 1, 4 and 4, 1, 3, 2. Let us select that one and consider as the parent for iteration 2. So let us take it as the parent 3 and 4. So you can see here that the other 2 parents are selected and we name it as parent 3 and parent 4. Again we are going to perform crossover similar to that. So again the crossover is performed and we obtained the child 2, 1, 3, 4, 4, 3, 1, 2. First we are going to check whether this root is available. So that is very important. We have to check whether 2, 1, 3, 4 and 4, 3, 1, 2 root is available. Yes, sir. We can see here that that root, whatever we have derived as a child, that is available. 2, 1, 3, 4 and 4, 3, 1, 2 is available. Next, we are going to check the fitness function. Let us evaluate. So in this iteration 2, so after the crossover, we have obtained two children, and let us name it as child 3 and 4. So let us 2, 1, 3, 4 and 4, 3, 1, 2. In this we have checked the path, so it is available. So let us, so the path is available. Let us calculate the fitness. Let us calculate the fitness function for 2, 1, 3, 4 and 4, 3, 1, 2. So we can see that it is 10 plus 15 plus 30. That is the cost of travel between 2 to 1 is 10, and from 1 to 3 is 15, and 3 to 4 is 30. So when we add, it comes to 55. Similarly, 4, 3, 1, 2. So the cost of fitness function comes to 55. So we can see that the cost is also effective. So we can see that from the table. If we see in the first table which we have framed with the 4 possible solutions, the fitness function, we can see that it was 60, 75, 70 and 75, and we can see that the solution we have obtained after iteration 2 is 55. So the cost is also minimum. So at the end of iteration 2, the process comes to an end with the possible least fitness function solution for the problem. So this genetic algorithm is applicable in many areas like control domain. Application type is gas pipeline, and in the design domain, where the application will be for aircraft design, keyboard configuration, communication networks, game playing, which is a very famous game, poker, checkers, and for security encryption and decryption, and also in the field of robotics. So I hope that this presentation had a brief understanding about the genetic algorithm. In future, we'll see how genetic algorithm is applicable to particular area. Yes, thank you.